Good day to all of you. I have been told by one of my students that I need to tone it down a little bit because my volume is much too high in comparison to what it should be. When asked if she turned the volume down on her computer, she said yes, all the way, and I still broke her eardrums. So, I will be toning it down a little. Anyways, with that said, today's lesson is on position and velocity. So this is our first real application of the derivative in calculus. If you have a background in physics whatsoever, if you've taken physics or AP physics prior to AP calculus, this is going to go a little bit smoother for you. But hopefully this fills in some gaps that you struggled with in those classes. So hopefully it helps you out. I guess before we get into actually doing problems and understanding how this relates to calculus, what we need to understand is the different ideas of what velocity is versus what speed is, and then how that relates to a position of a particle or a car or something like that. First off, speed is the rate at which you travel that is positive, the positive rate at which you travel. Because I can get in my car and I can drive down the road at 80 miles an hour, right? Now I could be traveling north or I could be traveling south, each of those at 80 miles an hour. Speed doesn't tell me which direction I'm traveling, it just tells me how fast I'm going. Speed and fast, those are related, okay? Speed and fast. That just tells me how fast I'm going, not which way I'm going, okay? Velocity, on the other hand, tells me the direction at which I'm traveling. So if I just say that I'm traveling 60 miles an hour, right? If I'm telling you that that's my velocity, I am telling you that I'm traveling 60 miles an hour in the positive direction, whichever way we define positive to be. So generally speaking, positive meaning up, or maybe to the right, or north, just as anchor points, right, directional, so we understand that. So the difference between speed and velocity are the same thing, with one exception, right? Velocity tells us which way we're going. So if we have a negative velocity, that means we are moving in the negative direction, okay? So understanding the difference between those two things is going to be vitally important. And in all reality, velocity relates to our position far better than speed does. Because if I'm, let's say I'm at home, I'm at the origin, whatever that is, and I travel north at 10 miles an hour for 2 hours, that would imply that I'm 20 miles from home in the positive direction. And then when I turn around and I head back home at a rate of 10 miles per hour, 2 hours later I will be back home. But if I only look at speed, speed is only telling me I'm traveling 10 miles an hour. And so after the end of that entire journey, of that 4-hour journey, the only thing speed is going to tell me is that I traveled 40 miles, right? Because I traveled 10 miles an hour, two hours this way and 2 hours that way, I traveled a total of 40 miles. It doesn't tell me where I'm at. It doesn't tell me my location. And so the position of something is directly related to the velocity of that thing, not the speed of that thing, even though speed and velocity are linked hand in hand. One just tells us the direction and the other one doesn't. So before we get further into this, we need to remember that what a derivative is. Remember, the derivative at a point means the slope of the tangent line or the slope of the curve at that point. So if I say, what's the derivative? Well, that's a function. What's the derivative function? That is a function that represents the slope at any point. But if I want the derivative at a point, that is the slope of that curve at that point, or it's the slope of the tangent line, okay? It's also known as the rate of change. Now remember, we talked about before that the rate of change, if I just say rate of change, I'm implying the instantaneous rate of change, not the average rate of change. So if you don't hear the word average in front of rate, then you are finding the instantaneous rate. You are finding the derivative, okay? And then the first application that we're going to see is that the derivative is the velocity. And I think it's pretty easy to comprehend that, pretty easy to see that the derivative of a position function is velocity. I think that just makes sense, that if I'm starting at home and as time goes on, I move away from my house, and then I get to a point where maybe I stop for a little while, right? And then I turn around and I come back home, and then maybe I stop for a little while, and then I drive in the other direction, and then stop for a little while, and then come back home. This is my position graph, okay? If I were to say, and then now I'm back at home again. So that in a sense, the t-axis represents our origin or our home place, our location. So we are 0 units from home, here, here, and here. Here we are on the right side or on the north side, or whatever positive is identified to be. We are on the positive side of the origin, and here in this interval we're on the negative side of the origin. But if I want to figure out the slope of this between, we'll just use the average rate for our example here. If I want to find the slope between these 2 points, this is the change in y over the change in x. So I'm finding the slope between these. But think about, sorry, not change in y over change in x, but rather change in x over change in t. So we're looking at this and thinking about units. If x is represented, or the units that are representing x, those might be feet or miles or something along that line. And time might be in minutes or hours or something like that. Okay? So this is how far I am away from the origin, and then this is how long it has been before or since I started counting time. So if I'm finding the slope here, the change in position, the units on that would be feet, and the change in time, the units on that would be minutes. And so you can see that the units are feet per minute or miles per hour or whatever it might be. You can see that this is a rate, and more specifically, it's a velocity. Velocity is some distance over some time, or the change in distance over the change in time. And so that's why velocity is the derivative of position. So that's something that you're going to want to consider. And we'll talk more about how that relates and how that helps us out as we go along. So here's an example of that. The graph below represents the position of a particle on a number line, x of t, in feet in respect to time, seconds. So you notice that the vertical axis, or sorry, the y-axis, if you would, x of t, is in feet, and then time is in seconds. This graph represents the position of a particle. It doesn't represent the speed. It doesn't represent anything else. It's a pretty basic graph. X of t is the position of the particle. So I'm going to go ahead and duplicate this graph here the best that I can. And if it's a little off, that's okay, we'll survive. Okay? So something like this. I always make my t-axis too short. All right, and then we have, at this point, we have 3. At this point, we have 6. This high point, time is 9. And then we have 12 over here. Again, not drawn to scale at all. And then we have, I better put this in. This height is 5. And this height is 10. And this height is 15. And then this height here is -10. Okay, so that's what we have here. Now I can ask a bunch of different questions, and we're going to just talk about how to interpret the graph in the context of position versus time. Okay, when is the particle furthest from 0? When I say furthest from 0, I don't mean furthest from this origin on this axis. I mean, when is it furthest away from what we consider home base. So really, this is kind of a number line, okay? This is our number line. It's just vertical instead of horizontal. 0, 5, 10, so kind of in the right, going right, and then negative 10 going left. The reason we have this other axis is because this particle is moving along. Maybe I should mimic this a little bit so we can see this. We have this, again, position, that's 0, and like that's negative 10, okay? Basically what we're saying is the position of the particle at t equals 0 is 10. Then at time 3, the particle moves to position 5. So it moves here, and then it stays there for a long time. It stays there for 3 seconds, and then it moves to 15, and then it moves to negative 10. And so really what this particle is doing is it starts at 10, and then it moves this way, and then it stops there for a minute, and then it moves this way, so it gets further to the right, and it stops instantly, basically, and then turns around and goes into the negative side of the number line. So you can see that we're trying to relate a one-dimensional number line to time here, and that tends to cause students a little bit of trouble. But anyways, the question is, when is the particle furthest from 0? 0 on the number line, not the origin on this graph. So when is the particle furthest from the origin? Well, just identifying some points, at t equals 3, the particle is 5, what was the units on this? This was feet. It's 5 feet from the origin. So 3 seconds in, it's 5 feet from the origin. 6 seconds in, it's 5 feet from the origin. 9 seconds in, it's 15 feet from the origin. And 12 seconds in, 12 seconds in, it's 10 feet from the origin. In this case, it's 10 feet to the left of the origin, but it's still 10 feet away from the origin. So when is the particle furthest from 0? It is furthest from 0 when t equals 9 seconds. Or furthest from the origin, 9 seconds into our journey, you could say. Okay? T equals 9 seconds. The next question says, how far is it? Well, how far is it from the origin at that time? Well, at 9 seconds, it is 15 feet from the origin. Again, the origin meaning 0 on the number line. Okay, so that was B, I guess you'd say. Okay. C, 15 feet. Okay, to the right. That's a good point. It's 15 feet from the origin, but it's 15 feet to the right. Okay. Next question, when is the particle moving to the right? Now, this is going to be a big concept in future lessons here. When is the particle moving to the right? The particle is moving to the right when it's moving in the positive direction. Not positive this way on this graph, positive this way, positive going up. Okay? When is it moving to the right? It's moving to the right when we see it going uphill, when we see the function increasing. So we would say it's moving to the right from 6 seconds to 9 seconds over that interval. Okay, 6 to 9 seconds. It is moving to the right. Okay? When is the particle moving to the left? Well, the particle is moving to the left when the graph is decreasing. It's decreasing from 0 to 3 and from 9 to 12 seconds. Okay? So it's moving to the left when you see the graph decreasing. Okay? And then the last question here, I believe, it says, when is the particle not moving at all? Now this is a interesting argument. Okay? When is the particle not moving at all? In other words, when is its position remaining the same? Well, the particle is not moving. I think it's pretty obvious to say from 3 to 6 seconds it's not moving because it started at position 5 and it stayed at position 5 for those 3 seconds, so it's not moving. Now, one argument somebody might say is up here at this point when t equals 9, what's going on there? What is happening? Well, the particle was moving to the right. The particle was moving to the right, And then from 6 to 9, it was moving to the right. And then from 9 to 12, it was moving to the left. So would that not imply that that particle stopped at t equals 9? Because if it didn't stop, that means it kept going in the same direction. Now we have to be careful here, because I would say that the particle didn't actually stop at t equals 9, because this is a nice sharp corner, what we talked about in the past, a corner. This function is technically not differentiable at t equals 9 because it's a corner. We wouldn't say that the particle stopped at that point, because it instantly changed direction. So it was moving in this direction, and then boom, now it's moving in that direction. There was no stopping, there was no slowing down, there was no moment of pause or anything like that. Whereas if the graph looks something like this, where it was smooth, okay, this graph is differentiable. At this point, watch what's happening. The steepness of the graph is mellowing out until the steepness becomes 0, until the slope becomes 0, and then it gets steeper again. It just gets steeper in the opposite direction. So what's happening here? The particle, or the person, whatever it is running along at some speed, and then it starts slowing down, right? And then it gets to a point, it stops, turns around, and then starts running again, and then and as it's running, it's speeding up. So it's going fast, and then it's slowing down, slowing down, slowing down. Let's do it this way. He's running fast, and now he's slowing down, slowing down, slowing down. He's stopped, he's turned around, now he's running again, and he's picking up speed, picking up speed, picking up speed, okay? Because the steepness of this curve is changing. Where here, this is linear, the steepness isn't changing, so the rate isn't changing. The rate is an exact value. The rate over this interval is up 10 over 3, 3.3 feet per second. And then boom, all of a sudden, the rate changes to negative 25 over 3 feet per second. So instantly it changes direction, whereas here, it slowed down, and then it sped back up again the other way. Okay? And in all reality, this is more applicable to life, because there's nothing that we can really say is instantly stops and turns around. Even if I throw a ball at a wall and it bounces off that wall, technically it is slowing down. It's not immediate, because the ball has some elasticity to it, to where the wall absorbs the energy of the ball, and so the back end of the ball really is slowing down as it hits the wall, and then the moment it hits the wall, it slows down, and then it speeds back up again. And so there is no real good example of this context in real life, but it's a good way to see it for now. Okay, so when is the particle not moving? We would say from 3 to 6 seconds. All right, last question here. When is it moving the fastest? Now, this is a good question. When is it moving the fastest? It is moving the fastest when its rate is the greatest, I guess you could say. But you got to be careful with that, because the rate can be negative. In this context, we're saying, when is it moving the fastest? Again, I tried to relate this earlier in the video. Fastest implies speed. When you hear the word fast, you think speed, not velocity. So we can calculate the rates along different paths. And since this is linear, we can go ahead and calculate this. We could say the speed, or sorry, the rate over the interval 0 to 3 is negative 5 over 3, or negative 1.667 feet per second. Okay, so that's the velocity over this interval. The rate, or the velocity, from 3 to 6, well, is 0, right? 0 feet per second, because this particle isn't moving. It's staying still. The rate from 6 to 9 is going to be up 10 over 3. So that's going to be 3.333 feet per second. And then the rate from 9 to 12 is going to be negative 25 over 3, which is what? Negative 20, that's be negative 8.333 feet per second. So here I figured out all the velocities. Now, because this is linear, the rate throughout this entire interval remains the same. If it was curvy, that rate will be changing, and that's where we would need the derivative, but not in this case, okay? Now the question is, when is the particle moving the fastest, okay? When is the particle moving the fastest? It's moving the fastest, well, what is the speed? We could say here, therefore the speed equals 1.667, right? The speed here is 0, and the speed here is 3.333, and the speed here is 8.333. Again, the emphasis is this: speed is the absolute value of velocity. They're the same thing, it's just one has a sign, one has signs indicating direction. Speed does not have a sign indicating direction. So speed is the absolute value of velocity. So when I say when is it moving the fastest, I'm looking for the speed, and we can see that it's fastest there. So we could say that it's moving the fastest from 9 to 12 seconds. That's when it's moving the fastest. Okay. Now, the last part of this question, it says, when is it moving the fastest? And then I say velocity. I don't know what that means exactly, just velocity. I don't know why I put that there, but I think what I'm saying is, when is the velocity the greatest? So this is when the speed is the greatest, but where is the velocity the greatest? The velocity is the greatest, let me identify it here. The velocity is the greatest here, because it's the greatest numeric value. It's the greatest positive value. So we would say from 6 to 9 seconds. And obviously, if it was, let's say it was like this, the curve looked something like this, when is this, when does this have the greatest velocity? The greatest velocity would be when the slope is the greatest, or when the tangent line is the steepest. So we would say right here, that is the greatest velocity, okay? So let me give you another comparison here. That would be if it was a position graph. Let's say I've got something that looks like this, okay? Something that maybe looks like this. Well, what is the greatest velocity? If this, again, is a position time graph, the greatest velocity is here, because that is the steepest positive slope. Because remember, velocity means slope of the position graph. This is the greatest velocity. Well, where is the greatest speed? Because again, speed is the absolute value of velocity. The greatest speed would be here. Why is that? Why is that? Because this is a negative velocity. This tangent line right here is steeper than that tangent line would be. It has a negative slope. That has a positive slope, so obviously the velocity is greater here because it's a positive value where this is a negative value. But when we're talking about speed, this is the greatest speed, because when you compare the two slopes of this, maybe the slope here might be 2 over 1 at that particular point. This slope might be negative 3 over 1. Because we're talking about speed, the speeds would be the absolute value of 2 over 1 compared to the absolute value of negative 3 over 1. Well, 2 and 3 absolute value, this 3 is greater than that 2. So even though it's going downhill, it's the greatest speed. So that's the difference between speed and velocity. Sorry if I belabored that. I realize that some of you might have an intuitive understanding of that, but I just see a lot of students struggling with that idea over time. So it's really good to kind of just preempt that and attack it before we really get into the lesson itself, or more applications of this. All right, let's go on to the next slide here. The next slide is going to be, the next slide is actually going to be relating this to the derivative graph. So what I want to do now is, same graph, this is the position time graph. What I want to do is graph the velocity time graph. So this is time in seconds again, but now I'm going to graph the velocity function, and the units on this would be feet per second, okay? So same intervals, we got 3, we've got 6, we've got 9, and again, I made my axis too small. We've got 12, Okay. So those are the key points here that we're going to be focusing on. And now these numbers are going to be different than those numbers because these are the positions. How do I graph the velocity? Well, remember, the velocity is the derivative of position. Put that in your brain. Don't forget it. The velocity is the derivative of position. And we have, in the past, graphed derivative functions from normal functions. Remember, one of the activities was here, the graph of sine. Here's the graph of sine of x. Graph the derivative of sine of x. And we did all the tangent line values and everything else, and we discovered that the derivative of sine is cosine. Well, we're doing the same kind of skill here. So we would ask ourselves, okay, when is the derivative? This is always a good way to graph derivative functions. You ask this, when is the derivative 0? When is the derivative positive? When is the derivative negative? So those are the three things you need to know. When is the derivative positive? The derivative is positive when the graph's height doesn't change, or when the direction changes, in a sense. So from 3 to 6, I'm going to go ahead and use the red marker so we can see it better. From 3 to 6, the velocity is 0. And you can see that. The slope of this guy is 0 because that's a horizontal line there. Anytime you have a horizontal tangent, you would have a 0. So if you can draw a horizontal tangent line anywhere, so if I was to look at this graph, and maybe I should, maybe this is what I'll do. I'm going to do a kind of a comparison between the two because these are all linear piecewise. Let's talk about more of a smooth graph here. And let's say 3, again, 6, 9, 12. And this will be a position graph again, x of t. And this will be time again. Okay. And let's make this a little bit smoother. So instead of just flat lines, let's make it smoother. So we'll go like this. Okay. So that's roughly, now this is obviously not differentiable at points because you have a bunch of corners. This is now smooth. So let's see what the difference in the two graphs looks like as time goes on. Well, we know that the velocity here is 0 over that entire interval because the slope is 0 over that entire interval. When I graph the velocity graph of this bottom one, 3, 6, 9, 12, we would say, where is the velocity 0? The velocity 0 at this point and this point, because I can draw horizontal tangent lines. Because the slope of the tangent line is 0, we can say that we have a 0 slope. So it looks like this point is maybe at like 4.5. So at 4.5, I have a velocity of 0, so I'll put a dot there. And then maybe it's 0 at 9, so I got another dot there. Okay? So that's when my velocity is 0, when the slope of the tangent line is 0. Now we ask the question, when is the velocity positive? The velocity is positive when the function is increasing. And think about it. If the function is increasing, you have a positive slope, which means you have a positive derivative. In this case, we can calculate that pretty easily, and we already did in the previous slide there. The slope here is positive from 6 to 9, and we can calculate that because that's linear. That's 10 over 3. So we can actually say that the slope from 6 to 9 is 3.333. Okay? All right. So this is 3.333 feet per second. Okay? Oops. 3.333. All right. And then down here, it's going to look a little bit different. Let's see what happens. When is the function increasing? The function is increasing from 4.5 to 9. So that means our derivative is going to have a positive slope from 4.5 to 9. So we know that our derivative is going to be in the positive region above the t-axis in that interval. Now, we don't know exactly where to put it yet because we can't calculate the slopes based on a curvy graph. We would need a function or something like that. But this is an important thing. When is this graph the steepest? In other words, when is the tangent line the steepest? The tangent line is the steepest maybe here. Okay? The tangent line is steepest there, which means the slope is the greatest there. So I don't know where that is. That might be like 6 points. Let's just say that's 7. So at t equals 7, what we get is a high point in our derivative graph, because that is the greatest rate that will move at. That is the steepest line, okay? Now, everything else within this interval has to remain positive. A good way to think about this in general is that if this is smooth over an interval, then this will be continuous over this interval. If this function is differentiable at all points, then the derivative will be continuous at all those points. Since this function is differentiable from 4.5 to 9, this one will be continuous. So we just want to make sure that we hit this point, and it's the highest point. That should be a 7, so I'll move it over a little bit. So maybe it looks something like this, right? Maybe it looks something like that. Again, we're not looking for too picky. We're just looking for the steepest point here to identify the highest point there. And then we want to remain above the t-axis because this is all increasing there. Okay, next question. When is the position graph decreasing? Wherever it's decreasing will tell me when my velocity is negative. Well, we see that this graph is decreasing over the interval 0 to 3. The slope for that was negative 5 over 3, so it's negative 1.667. Negative 1.667 from 0 to 3. And again, because this is linear, it's a constant slope. Anytime you see a line there, you're going to see a horizontal line on the derivative. Down here, it gets more complicated. Where is this graph decreasing? This graph is decreasing from 0 to 4.5 and from 9 to 12. Oh, we'll get to the 9 to 12 part in a second. From 0 to 4.5, we know that the slope is going to be negative. It's going to be down here from 0 to 4.5. The question is, well, what does this graph look like? You got to ask yourself, when is this graph the steepest? This graph in particular is steepest at the end point. Like that tangent line is steeper than all the other tangent lines. So that would imply that that slope is the greatest negative number, or the furthest down in this graph. So we would graph it something like this. We would put it at a low point here. And because all the tangent lines, slopes, all these tangent lines after it are starting to flatten out, that means that this is starting to approach, the slope is approaching 0. Okay? So this is, again, not going to be great, but just an idea. So it's steepest there, so this is the lowest point. It's steepest here, it's the highest point. This slope is starting, or this line's flattening out, the tangent line's flattening out, therefore the slope is approaching 0. So you can see the value of the slope, or the value of the derivative, is approaching 0. It's approaching the t-axis. Okay. Now let's go back up to this one. From 9 to 12, we said negative 25 over 3, so that's negative 8.333. That's actually going to be, get rid of this here. That's going to be down here, negative 8.333. So from 9 to 12, there is the graph of our velocity function, if you would. Okay. Now going down here, again, this is decreasing. Therefore, this is going to be negative. So from 9 to 12, it's all going to be negative. Okay. Where is this graph the steepest? In this particular case, the graph is steepest, it looks like, at the end again. Now, it seems pretty consistent, like it's kind of staying the same there, like from here to here, it's kind of the same thing. But regardless, at 12, maybe it's the lowest point. And notice that this point is a lot steeper than that point, which implies that it has to be a lot further down on this. Now, we know all of this is going to be negative. We can see at 9, the slope is 0, and it gets steeper and steeper and steeper, and therefore this graph is going to start at 0 and get more and more negative, more and more negative. And so we have a graph that maybe looks like that. Now, generally speaking, if you just think of patterns, these graphs, in a sense, look similar to each other, going down, then going up, and then going down again, going down, and then up, and then down again. So you would think the derivatives look similar, and they don't. But one thing that does look very similar is that wherever this was 0, this was 0, and wherever this was positive, wherever this was negative, this was negative. Okay? Like I said before, when you have a graph that you're trying to take the derivative of, and you're trying to graph that derivative function, whenever you see horizontal tangents, the slope will be 0 here and here, right? Horizontal tangents. Whenever you see the function decreasing, you'll see the derivative graph negative. Okay, decreasing, decreasing, negative, negative over the same intervals. Whenever you see the function increasing, you'll see the derivative is positive. Okay, increasing from here to here, so positive. So that's number one, or number two. Number three, to graph a derivative, you have to ask yourself, especially in a smooth graph, where it's the steepest. Wherever it's the steepest within each of these intervals will be either the lowest point in that interval or the highest point in that interval. Okay, so we say, okay, it's decreasing here. Within this interval, where is it the steepest? It's steepest at the end, so we put the lowest point there. Where is it in this interval? It's increasing from 4.5 to 9. Where is it steepest? It's steepest here, therefore we put the highest point there. Where is it steepest over this interval? Well, at the end, so we put the lowest point there. Okay? Now these are very rough graphs right now. We will get more detailed as time goes on, but that's the idea of graphing derivative functions. Now, that's the end of the lesson, but there is a PDF that has a bunch of practice problems that are related to this, that have some piecewise where we have some linear pieces and some curvy pieces, right? So what I want you to do is look at that link, and I want you to work out those graphs, and when we meet live, we can go over those graphs and make sure we understand them. But hopefully you got an understanding, a little bit better understanding of graphing derivative functions, and a good understanding, at least for the level that we're at, of understanding the relationship between position and velocity. So until next time, I will try